just let Tricia do the honors.
Yeah, we just start the live. I hope YouTube don't block me.
Should I share screen?
No.
Yes, please. Just a second. Just double checking we are live.
Does this work?
It's still connecting there. Yeah, the sharing of the screen is okay. I'm just making sure the live is on. Let me just refresh the page. Doesn't seem to be live. Let me That's weird. Sorry about it. Adrian, can you check if we are live or not? Because it seems that we are live, but I don't see the image on the YouTube. We are live. We are good. Thank you. Okay, sorry about it. Okay, so good afternoon or good evening, everyone. Welcome again to this Quantum Matter seminars today with Lawrence from University of Ghent. And he's going to talk about his recent paper on a method for evaluating spectral functions in momentum space using matrix product state. So thank you very much, Lawrence, for accepting our invitation. The stage is yours.
All right, thanks a lot. And of course, thanks a lot for inviting me to this great seminar series. So I'm going to talk about the recent paper that we've written on evaluating spectral functions with MPS, essentially. And so this is the overview of my talk. I will first give a motivation on why we're actually interested in calculating spectral functions. And I will start with explaining how we actually introduce momentum in MPS simulations and how we can use this to get information about excitations in strongly correlated quantum matter using this momentum resolved methods. Then I will quickly explain how people typically in the context of MPS typically compute spectral functions using time evolution in real space in order to set the stage for then explaining how we do it in momentum spaces. I will show that it's indeed a lot more efficient to do it directly in momentum space. I will give you, I'll try to convince you of that fact. And I will explain you a bit how we do it. And then finally, we will discuss some results and give a quick outlook. So if there's any questions, please do interrupt me at any point. If something is unclear, please do interrupt me. So let me just first thank my collaborator, Maarten van Damme, who is here in this picture with me. Actually, it's a picture of me Maarten, and the King of Belgium. But obviously, well, to be clear, the King was actually not involved in this project. So, right. So let's start by giving a short motivation. So, so in spectral functions are well, arguably like the most important probe for actually relating theory and experiment in the context of strongly correlated quantum matter. So generically, a spectral function looks like this. So it's a momentum resolved, frequency resolved correlation function. And it's, well, the reason why it's so interesting is because it's like a direct probe for the lower lying excitations in your system. If you cool the system enough, you go into the ground state, and then this probes sort of the low lying excitations on top of a ground state. So a very famous example is inelastic neutron scattering for magnetic materials. So these are, well, this is an example of a famous experiment where they actually did neutron scattering on a 2D cargo spin liquid, and they saw these in these spectral functions. You can basically see some kind of continuum rather than a sharp mode in the spectrum, which is really one of the hallmarks of spin-on excitation. So you see a continuum of excitations due to this, the fact that you always excite multiple spin-ons in the system. This was really the first time that they could sort of show that the material realized some kind of spin liquid. A very beautiful example of how theory and experiment actually can relate by looking at the spectral function is this example of a study done on the one-dimensional Heisenberg spin chain, where they did experiment and theory, and they saw this very nice correspondence. So this is, well, for the 1D Heisenberg spin chain, you can do you can use integrability or the beta onsets to actually do this theoretical evaluation of the spectral function. And this is what we would like to actually achieve in the most general case for, like, for example, for 2D systems as well, to have this beautiful relation between theory and experiment. And for that, I mean, for achieving such a thing in a more generic case, we really need like ways of computing the spectral function and starting from the microscopic Hamiltonian, essentially. And this will, I mean, giving this nice correspondence, we can sort of claim to understand this material, for example, in a thorough way. Another example, of course, is ARPES for electronic systems, where indeed you see whole spectral functions. And for example, in this experimental paper, they saw some, well, maybe some evidence of spins charge separation in the cuprates. And again, this is like in ARPES, you measure basically the whole spectral function. So this is what we would like to achieve. To be able to compute these quantities from just the microscopic Hamiltonian. So a very specific example that I worked on together with the group of Michael Knapp in Munich is the Hubble model on the triangular lattice. So this is, well, in the last years, this has been sort of studied in some detail because as a function of this interaction parameter, people observe that there is some kind of chiral spin liquid phase in between the sort of ordered magnetic insulator and the metal phase. You have this sort of exotic chiral spin liquid, which is emergent. So there's no time reversal symmetry breaking in Hamiltonian, whatever it is. So the chirality is really an emergent feature here. And people, well, believe that this chiral spin liquid, this leads to deconfined spin-on excitations and maybe spin charge separation in the system. So we wanted to look at this. So we computed the whole spectral function to see whether actually in the spectral function there's some signatures of this spin charge separation. And what we see is, well, if we look at the ordered phase, so that very large U, we essentially in the whole spectral function, we essentially see a hole dressed by spin fluctuations. So it's nothing that interesting. It's just, well, we have basically a free electron dressed a bit with the spin fluctuations in the background, but nothing too dramatic. But if we go into this chiral spin liquid phase, then we see something completely different. And what we actually see is something that agrees very well with the Parton mean field approach for this model, which is supposed to indicate that what we're actually observing in this dispersion of the hole, or the charge carrier, if you want, is the dynamics of a single spin-on. So the idea is that this electron or this hole separates into a spin-on and a holon, and this holon is a very heavy thing, whereas the spin-on is really determining the dynamics of this sort of composite. So this was, I mean, an exciting result in some sense. But in order to actually compute these spectral functions, this was a very heavy calculation. We were limited. So we used MPS, time-dependent MPS simulations. but we were limited to like a 3-lag cylinder for this system, just because it was too expensive to actually go beyond a 3-lag cylinder. And that's really sort of the motivation. This was at least my motivation for looking at whether we can actually find something more efficient, because just on 3-lag cylinder, this was almost, I mean, this took weeks of simulation time. So it's like, the question is, can we do better? And then, well, the question is, of course, let me just, well, what sort of methods are available to compute spectral functions numerically? So of course you have exact analyzation, but this is limited to even way smaller clusters. Of course you have quantum Monte Carlo, but even for systems that do not have a sign problem, the analytical continuation is something that's often like not too well conditioned. So, well, you can do stuff, but it's not fully under control. And then, of course, you have matrix Pollock states where you have different approaches. But here we will focus on this on real-time evolution that you can.
It's frozen. It's just me.
That
Sorry, Lawrence.
So yeah.
You froze for a few seconds.
So yeah, it says here that my connection is unstable indeed. Okay, I'm back, or?
Yeah, you're back. I think the last part was the real-time evolution.
Yeah. So so we use real-time evolution. Wait, let me just. I will just put this Wi-Fi off. Yeah, okay, I'm back.
Yeah.
Yeah, so this should be a more stable connection. Yeah, so the problem with real-time evolution is that you need huge computational resources, essentially because you have a dramatic growth in entanglement as time evolves. This requires huge bond dimensions in the MPS. I will talk about this in detail. And this basically means that you're limited to very small cylinders in practice. And in this talk, we will try to find a way around this, or at least sort of make the problem a bit less severe. So that's what I will talk about. And the way we will actually target this, or try to do this, is by first realizing actually that all the MPS methods that are typically used, they all break translation symmetry in some way. So this is a bit strange somehow, because the spectral function itself is a momentum resolved quantity. So this is a quantity that actually contains like translational symmetry as some kind of a fundamental thing. And this is what we will try to do. We will use the momentum as a good quantum number in our simulations, as we're supposed to do in MPS, because we will always want to use as much symmetries as we can. And then I will show you that this actually helps a lot if you do this. Right. Are there any questions at this point, or thoughts? Or no? Okay. So the first way of using momentum in MPS simulations is by what we call like the quasi-particle onsets for capturing excitations in the system. And I will go in a bit of detail of how this actually works. So so the idea of MPS, I don't know whether like most of you are actually familiar with MPS or matrix Pollock states. The idea is that, well, you take a spin chain, and the beautiful thing of tensor networks in general and MPS in particular is that the ground state of such a spin chain can typically be represented by can be represented very efficiently using MPS. So what you see here is like a tensor A, which you just repeat on every side in your spin chain. And what you do is this tensor has like 3 indices. This outgoing index is like this spin degree of freedom, and these virtual degrees of freedom. So it's like a 3-lag tensor, and these virtual degrees of freedom, these are sort of summed over or contracted, we say, And this yields then sort of a microscopic states on an infinite system. Actually, you just sort of suppose that this goes on forever. And this dimension of this internal lag that you sum over, this is what we call the bond dimension. And the idea is, if you grow this bond dimension to large enough, then you can basically represent any sort of state efficiently. You just have to optimize variationally over this tensor, and then you find very good ground states for any sort of gapped model, but even for critical models, this works very well. So that's the ground states. So the idea of this excitation ansatz or quasi-particle excitation ansatz is that if you look at isolated lines in your excitation spectrum, for example, in this plot, this is the excitation spectrum of the spin 1 Heisenberg chain, and you have this very well-defined magnum mode here. It's so it's like a momentum energy plot, and there's this isolated line here, and it appears that you can describe this extremely well using these variational states. So what you do is you basically just at one site in your system, you change your tensor to a new tensor, and you take a momentum superposition out of this. It's like almost like a block wave with a certain momentum of a localized perturbation somehow. And what you do is you just optimize over this new tensor B. You make sure that it's orthogonal to the ground state, of course. And if you do this, you find basically your excitation energy as a function of this momentum that you have put in. And the variational energy that you find is really the excitation energy at a certain momentum. And if you actually have optimized this, you have the variational states, so you can also compute the spectral weights of these states, and you can see how they appear in spectral functions. So the nice thing about this is somehow a bit conceptual, is that this sort of ansatz gives a very natural interpretation of your excitations in the system as some kind of quasi-particle, because it's a local thing in momentum space on top of some kind of correlated MPS ground state. So it's some kind of an effective particle, so to say, on your state, on your ground state. And it's also very nice numerically in the sense that you can get, for example, for this Haldane gap in the spin 1 chain, you get more or less like 10 digits of precision at relatively small bond dimension. So like bond dimension 200 or something, you already get this number of degrees, of digits of precision, if you want, for this excitation energy. So this really means that this is the ansatz for describing sort of these isolated lines in the spectrum. So an example of this, like a real life example of where we actually use this, is in some kind of material by some compounds that, some people, experimentalists did inelastic neutron scattering on. And what they saw was these kind of, essentially isolated lines in the excitation spectrum. So they saw a few sort of bound states, if you want, of spin-ons. Well, they interpret this as bound states of spin-ons, but what you basically see is a number of different modes. And so this means if you have these sort of isolated modes, this means that this excitation ansatz will work very well for describing these states. And what we did is just applied. So we wrote like an effective spin chain Hamiltonian for this system, and we found basically these different. So we looked at like one momentum cut of the spectral function. This is plotted here. This is the experimental data, and then we did this quasi-particle ansatz for this, and this agreed very well. So there's a slight offset due to some experimental reasons that I don't really understand. But the different modes you could see very nicely. And just to give an idea, with time-dependent MPS methods, this was very hard to resolve actually, because it's getting these different peaks. You need to go to very large times to actually resolve these different peaks. But with this quasi-particle ansatz, you get this almost for free. So this, shows that this works quite well. Another example that we're working on right now, together with the group of Frank Polman and Roderick Missner, is the triangular lattice Heisenberg model. And we do this on a 6-leg cylinder, such that we can use like MPS on a cylinder. And we actually use both time-dependent MPS methods to get this spectral function. And then we also use this quasi-particle ansatz, which gives you this line of excitations. And you see, indeed, if you have these isolated sort of lines in the spectrum, that this excitation ansatz gives you this sort of these modes quite well. And this is very useful because, I mean, to just give you an idea, these time-dependent MPS methods, they are extremely expensive. So this really takes weeks of simulation time. But this quasi-particle onsets is something like you can do this on a few hours on a simple desktop, essentially. So this is a lot cheaper to actually compute it like this than using this the sort of more standard ways of doing it. But let me now go back actually to this Hubbard model on a triangular lattice that I talked about before. Then we also did this sort of variational MPS method that we call it here, like this quasi-particle onsets. And now you actually see what the problem is a bit with this onsets. The problem is that what this essentially does is always find the lowest lying state with a certain momentum. But if you actually have some kind of continuum of excitations, what it will find is basically the lower edge of this continuum. And this is not very useful in this case, for example, because it doesn't filter out like the relevant sort of modes in your spectral function. It only shows you like the lower edge of your continuum. And it can be that this lower edge has very low spectral weight, and it's not very interesting to actually know this sort of edge. Especially if you're interested in sort of the dynamics of the dominant mode in the spectrum. So this is very annoying, and this, well, sort of motivated us of finding something that actually allows you to also use momentum, but then also allows you to find like really this full spectral function somehow of a generic system, and a method hopefully that will not take will not cost you like 3 weeks to compute just on a 3-leg cylinder. Hopefully that's a bit of the hope. Okay, so let me now just quickly discuss like how people simulate spectral functions, like well, more or less standard way of doing it in the MPS community by doing time evolution in real space. So what people do is, or I mean, what I have also done is we compute the real space and real time correlator. So both in real space and real time, you just compute S of n and t. So what we do is we basically start from the MPS ground state, which we assume to be more or less exact. And we apply a local operator, so this O of O(n), so at the site n. And then we just do time evolution on this state. And if you think about this, well, what do you want? What will actually happen if you do such a time evolution? So the idea is, if you look at this, you apply a local operator at time 0. So what will happen is actually that some kind of the signal will just spread through time in space, and it will generate just a whole bunch of different excitations in your system. They will all be entangled and they will travel at a certain velocity if you want. But actually a lot of different velocities in the system will probably contribute. What you will find after a certain time is just a whole bunch of a mess of different excitations that have been excited and are just traveling around in your system. They are colliding and everything they want. So what you would actually need to represent this is some kind of, if you look at your infinite state, what you would need is somehow something that is, well, look, an MPS that is localized around the state, but has some kind of sort of finite width, which is supposed to grow as time progresses. And this is what we sort of model with a window MPS. We call this, like, it's on top of your sort of infinite MPS background. We take a number of different tensors in some kind of region that we allow to change as time progresses. So for the experts, what we do is we just take some MPO approximation of the time evolution operator, and we do some kind of sweep optimization for every small time step. It's not really important, but for the experts that would like to know what we actually do, that's what we do. And then if you actually are able to represent this state, this time evolved state of this local operator as this sort of window MPS, what we can do is just measure the correlation functions again with the ground state. This is the sort of the easy part. And once we have this S of n and t, we basically Fourier transform to momentum and frequency space, and we find S of q omega. Now, this sounds all very nice, but as I said, this sort of time-evolved state is a whole mess of different excitations and different things. So the question is, can we actually represent this state efficiently, this time-evolved state, using this sort of window MPS? And indeed, this will turn out to be the crucial approximation, which is not, well, as time evolves, at some point will break down. And I can give you a very specific example of this. So again, we look at the spin-1 Heisenberg chain. This is a spectral function of the spin-1 Heisenberg chain. If you want, you have this dominant magnum mode, but then here at low intensities, low momenta, you have this 2 magnum continuum. And there, this is actually sort of the harder part of the spectrum to approximate. So let us look at this momentum cut and let's look at S of QT. So for this momentum, we look at the time signal. So we have already sort of transformed into momentum space, and we look at the time signal that we find with our MPS method. So we did a benchmark simulation at the bond dimension of 2000, if you want, just to have the sort of exact result. And then we just repeat the same experiment, but now with a very low bond dimension. And this, I mean, this sort of experiment shows you that indeed you can do this time evolution efficiently, but only up to a certain time. And then at some point, since you have created all these different excitations in your system, at some point your approximation will fail because the bond dimension is just too low to represent this time-evolved state well. And then, well, it will do some sort of random stuff as time evolves again further. And if you sort of Fourier transform this to frequency space, what you will find is, well, a spectral function that looks a bit like it's supposed to do, but with some indeed very strange artifacts. And indeed, the idea is that, well, at a certain time, well, here time 5, if you want, this is not the same model, but it's like you will just not be able to represent this sort of this mess of particles that you have created anymore with a certain bond dimension. And the question is, okay, can we do better? And this is where this time evolution in momentum space comes in. The idea is that instead of, well, taking the fact seriously that the spectral function is actually a momentum resolved quantity. So what you do in a spectral function is actually apply a momentum operator to your state and time evolve this one. So what we do is we write this sort of S of Q omega as a Fourier transform of this sort of return rate of this or this time evolved, the overlap of this time evolved state with your original momentum state, where this psi qt is, well, your sort of momentum space operator acts on the ground state, and then time evolved this one. And the idea is, well, we will approximate, well, it's very similar to what we did before. So we will take a momentum, a sort of a window MPS, but now we will actually use the sort of momentum space version of this. So we take the momentum superposition of such a momentum, of such a window state. And you might wonder, can you actually simulate this? So I will not go into any details. What we do is, again, very similar. We just do a variational update of it after any small time step. And it appears that you can actually do some kind of gauge fixing of the tensor as you usually do in sweeping algorithm. So you can just sweep over these different tensors as you're used to in any MPS algorithm to do your sort of variational update for every time step. That's very, I mean, that's for the experts again. And it's only the cost of actually working with this momentum superposition is just a sort of an extra linear scaling in the size of this window. So it's not too bad, so to say. It's actually, you can even parallelize actually over these different, over this linear scaling. So if you have enough CPUs, so to say, you can basically do it at the same cost as a real space, as the real space version. And if we actually look at the results, so does it help by actually going to this momentum space version? It appears that for isolated lines in the spectrum, this momentum space window works actually up to infinite times somehow, because we know that such an isolated mode in the spectrum can be represented very well by this quasi-particle excitation ansatz that we had before, which was essentially just a momentum superposition of a local perturbation. So we knew that these modes were essentially live exactly in the subspace that we actually use to represent the time evolution. So we know that this will work more or less perfect. But the real question is, of course, what about the continua in the spectrum, which is a lot harder to do. So we take the same experiment that we did before. So the real space version at bond dimension 50 broke down at times 5 or something. So if I actually look at the momentum space version of the same bond dimension, we see that we basically can evolve this up to, well, the times that we just took as time 30 here, without making any errors. So this, and then also in the well, obviously in the more in the frequency version, this gave like a very nice line shape using this momentum space window. So the reason why we were a bit surprised by that it works so well, but the reason is, of course, that by sort of filtering out one momentum mode, so we work with one momentum, we never break transition invariance in this approach. We sort of avoid this scenario that we had here, whereas we just create something local and we can just create excitations at all different momenta and they just interact and collide or whatever. By doing something in momentum space, you basically filter out one mode and you basically transform away also already sort of the global momentum of the excitation that you made. And the only thing that you have to sort of keep track of now is basically only the relative momentum, for example, between these two. This is like a 2 magnon continuum. So what we basically have to represent in our momentum window is some kind of the relative motion between the 2 magnons in this state. And this, well, already gives you a huge computational benefit of in this case. Right. So this was a bit just a test case, just to illustrate what this method does on the spin 1 case. So let's now look at a bit more of a challenging model. So we just took the XXZ chains, which is an entanglement model, and it's critical. So we took some kind of parameter which is in the critical regime, and which, well, if you use beta onsets, like Jean-Sébastien Sarko is of course the guy who did all these calculations, you see that you get some kind of gapless excitation spectrum with some, well, continua of multi-spin-on excitations living here. And so what we did, we just took one momentum cut of the system at pi/2, like over here, and we looked at the line shape of this spectral function. And then you see, well, first let's look at the time signal. So I just give you like a short time interval from, well, it's a bit arbitrary units, but it's like time 60 until time 70. Then you see indeed again the same scenario. It's a bit less clear somehow because the sort of the real space version is still oscillating at the right frequency somehow, but it clearly is already quite off. The sort of the real space MPS result, whereas the momentum space version is again sort of quasi-exact still at this time scale. And so again, in the sort of the line shape of your spectral function that you find at this momentum cut, using your momentum space window, you basically get very nice results, whereas the real space version gives you some kind of artifact that you don't really want. And this was at the bond dimension of 100, I think, something about this. So again, at a very low bond dimension, you get very nice results using this momentum space approach. Right. And then as a final sort of application, we looked at the J1, J2 Heisenberg model, but now on a 6-leg cylinder using MPS that you just twist around the cylinder. I wanted to look at this the spectral line shape for this the M point in your Brillouin zone. So have been a few experiments, well, mainly this experiment, where they looked at this. And they observed that there is some kind of weird thing happening to the spectrum at this point in the Brillouin zone. There's some kind of dip in excitation energy. Well, there have been different proposals of explaining this, but one proposal was that this is somehow some kind of precursor of spin liquid physics that you already see this experiment is more is for just the nearest neighbor Heisenberg model essentially. But so it's not in a spin liquid phase, but somehow they explained this sort of strange behavior here where basically your signal vanishes completely as some kind of precursor of spin liquid physics that already happens in the square lattice Heisenberg model. And the idea is, if you tune the J2, just sort of, if you add frustration in your system, you add a J2 interaction to your square lattice Heisenberg model. The idea is that, well, basically your spectrum will completely bend down, and you will develop some kind of gapless Dirac point that is somehow the hallmark of the U1 spin liquid that's supposed to arise if you tune this J2 interaction to 0.5. This is what what people expect that will happen, but it's very hard to compute this numerically. Also, I don't think there's any experiments that can actually probe this, but okay, people do expect this from field theory, I guess. So the question is, can we simulate this? So we did this. We first looked at it at just a pure nearest neighbor Heisenberg model, so without the J2 interaction. And we observe basically some kind of, well, S of q omega, which is, well, the gap, for example, that we find. So the excitation energy here is more or less an agreement. Well, it's actually quite exactly in agreement with other numerical approaches like quantum Monte Carlo for this point. But then if you look at J2 is 0.5, which is supposed to be in a spin liquid phase, you see that, well, the spectral line shape has shifted away significantly to lower frequencies, but still, it still shows quite a big gap. Actually, it's like of the order 1 still. So this shows. So we checked whether, of course, our result was actually correct, and indeed we saw that it's more or less converged into bond dimension in terms of bond dimension, and so we believe that this result is really what you would find for the 6-leg cylinder. But this clearly shows that somehow the gapless nature of your spin liquid. So what we expect here is actually the Dirac point here, so a gapless point. We don't find this, and this is most probably just a huge finite circumference effect. The fact that we're working with the 6-leg cylinder leads to quite a significant gap still in your system. This is, by the way, also in agreement with variational Monte Carlo studies of the same model, and they basically assume that there is a U1 Dirac spin liquid, and they see putting the system on a 6-leg cylinder really sort of opens up a gap that is quite large. So the real way of going forward here is I guess to go to larger cylinders, and really, so just to give you an idea, this was not the most heavy calculation somehow. This was just sort of a showcase for that this method works actually. But I think if you really sort of invest a lot of computational effort in this, you can really sort of improve on this and maybe go to larger cylinders and get better results there, hopefully, and then maybe see something of a Dirac spin going there, or a Dirac point. Okay, so this was the main results that we have so far on this method. We believe that it's actually very useful, and I think the way of looking at these different methods of computing spectral function is basically to see them as complementary methods. So as I tried to explain you, this quasi-particle onsets is very super efficient for actually computing isolated lines in your spectrum, whereas real space time evolution has a great benefit that actually allows you to get the full spectral function in a single run. So you get, because you do something local, you basically get all momenta in a single simulation. And the great benefit of doing momentum space-time evolution is that you have a lot of more precision if you're actually interested in very fine-grained line shapes for a certain momentum, or you're interested in a certain Dirac point, for example. You really want to sort of get this very accurately. Then I think this momentum space time evolution approach is actually a very good idea to try. Of course, I've only talked about time evolution. There's other methods around which allow you to use to compute spectral functions using MPS, and we're currently looking at whether we can use, for example, correction vector methods in combination with this momentum space approach. And of course, we can try to use extrapolation techniques to somehow extrapolate our time signal to get better resolution using, for example, linear prediction, or this recent sort of recursion method that was introduced recently by Steve White, I think, and co-workers. So indeed, on that front, there's also a lot of progress to be made, I think. Now, I sort of want to conclude with saying that actually for 2D models, somehow MPS methods are actually very, they allow you to do things that you cannot do with other methods. But I think the really way to go is actually using PEPS methods for spectral functions. And I want to just, like, with 2 minutes, I want to sort of give an outlook on what we actually want to do with PEPS. So PEPS, these are projected entangled pair states. So these are more or less the straightforward generalization of MPS to 2 dimensions. So you just take a 4-leg tensor now, you put them in a square lattice grid. This would be the ground state of your system. And it appears that this quasi-particle excitation analysis you can just do this. We did this. You can optimize this using a PEPS ground state and then compute the excitation spectrum. So we looked at the 2D IGZE model and got very good results. And recently, the Amsterdam group used this approach to compute the Arbeit spectrum of the 2D Hubbard model. And the group of Tao Chang also did a very recent work on the triangle lattice Heisenberg model using PEPS, using this quasi-particle excitation ansatz. So this actually worked quite well. But the same problem that we had before is also here true, in the sense that you cannot really compute like continua using this excitation ansatz. So the real sort of question here is whether we can just extend our momentum resolved time evolution approach also to PEPS. And I think, I think in principle it's doable. This is definitely something that we will try in the future. And with this, I would like to thank all of you for listening to the talk. And if there's any questions, please go ahead.
Thank you very much, Lawrence. Very nice. Maybe I'll start having a question. So in principle, to reconstruct the momentum resolved spectrum, you can just run all the Qs in parallel, right?
Yes. Yeah, indeed. Indeed. And as I said, if you have enough CPUs, this is definitely the most efficient way of doing it. You can just do it parallel. But but indeed, if you want to be a bit efficient and just get a general idea of the full spectral function, then it's probably a good idea to do it first in real space to get it in a single run. And then if you're interested in a specific momentum vector, maybe you can do this momentum space version. That's, sort of the workflow that I would have in mind.
Okay, so we have 2 questions. I will leave it to Stephen.
Hi, that was very, very nice.
Thank you.
Let's see. So just one possible suggestion in the J1, J2 model, where you still saw this big finite size gap. Have you considered any sort of, fancy boundary conditions around the cylinder?
Of the type of that Pohlmann and Zaletel used for some kind of magnetic, some flux that you introduce to
right.
We thought about this, but we refrained a bit from doing this because this breaks the SU2 symmetry of the model. It's like and then we cannot sort of exploit SU2 anymore. That's the reason why we didn't even do it at this point. But indeed, this is one of the ways to go to actually resolve this Dirac point better. Indeed.
Great.
Noah, your turn. I think we cannot hear you.
We take the background state. Can you hear me now?
Yeah, sorry.
Yeah, we cannot hear you. No, I think you have to put your volume, go a little bit louder.
You can put it in chat maybe if you.
Yeah, maybe you can.
Can you hear me
type
now?
your question.
Yeah.
Now you can. Yeah. Thank
Okay,
you.
okay. I was using a microphone, it wasn't working. Okay.
Oh,
So now I'm
sorry.
using the computer. Sorry about that. Okay, so the 1D Heisenberg equals 1, Steve's old the Haldane gap, right? There's a kind of a new guess about this Haldane gap. It kind of goes back to Haldane's work on some other things in 2D from a while back. The guess is this, that we take this matrix product state, from the ground state, and, kind of multiply a bunch of them together to kind of do like half the system, right? And then, calculate the singular value decomposition for the left-hand side compared to the right-hand side. Like what you would do to calculate the entanglement entropy, but instead you kind of look at the spectral, the eigenfunctions, and compute the spectral function as though it were a kind of a Hamiltonian for a finite temperature system.
Okay.
You hear me? Okay, and so the conjecture is that although the Haldane gap is gapped and all that, its gap is small enough that it's feeling the SU2 level 2 WZW model quantum, in the field theory language, the quantum phase transition to the boring phase, to the trivial phase, And so the new conjecture, the new Haldane conjecture, the gapless conjecture, is that the finite size, right? Because you do the finite size spectral functions that from the ground state, SVD for like half the system, that those will correspond to the finite temperature excitation spectrum of a real system at the critical point with boundary conditions that you have to specify. There's some details about what the boundary conditions would be. So I wonder if you have thought about checking that, because what it's trying to tell you is the spectral function for that critical point. That's that your phase is kind of the mother of your phase. You're in a gap phase, but you're near a critical point, right? And so this is a guess. It should hold in any dimension, but in one dimension we have some control, right? So I'm wondering if you've thought about. There's two questions. One would be to calculate in 1D the finite temperature spectrum, right? Then you can compare this thing. And the second is whether you thought about this SVD conjecture. It's about 3 years old. It goes back to Shinsei Ryu, Gil Cho, and Andreas Ludwig. So I can send you the link.
No, it sounds very interesting, but I haven't thought about this. But one thing is, of course, that you would break, if I understand correctly, that you would break translational symmetry. That would be some kind of half chain version, right?
We're just working in the ground state, just ground state. So you take the ground state, and so cheap, exact. Take the ground state, and now compute like you do for entanglement entropy. But look at the eigenfunctions come out. Don't just sum over the eigenvalues with the L log L or whatever. But look at the actual spectral functions.
Yeah.
And the claim is that those spectral functions are the finite temperature spectral functions of the critical point that separates you from the boring phase. Let's say you're in a Haldane gap phase. There's a boring phase, right? The one that's connected to the atomic limit. The claim is that critical point is kind of, they have all the critical exponents and all that. We know.
Sorry, I think you're
cutting out there.
Yeah.
Yeah. So I'm just saying that what we're thinking about taking of this.
No, falling away again.
So talking about using the ground state.
I think I will definitely. Yeah, it's a good idea, and I didn't know about this, so I think it's possible to compute such a thing. Yeah.
But what about the finite? I wonder if you could define it for guy like spin 1/2 Heisenberg at finite temperature. If you thought about doing that, the spectral.
Yeah, we can't hear you. I think
I
I'm
think
not yelling on
his question is about doing the momentum resolved spectrum of a system at finite temperature.
Yeah, doing the finite temperature version is definitely possible. Just using some kind of purification approach. This is more or less well established in MPS simulation how to do finite temperature. So that's definitely possible. Yeah.
Okay, so no more questions. Okay, if there's no more questions, let's thank Lawrence again. Thank you very much for this nice talk.
Yeah, thank you for having me, of course.
And next week is the March meeting, right? So we don't have a seminar. So we go back the week after the March meeting. So see you.
Right.